Hello, I'm Rhett Davis from NC State University, and I'd like to talk about heterogeneous 3D design with OpenAccess. Much of this work was performed by Ziyu Deng, who is a graduate student at NC State when he was performing his internship at SI2 last summer. These are stacked 3D systems, such as the one from Intel pictured down here, which contain chiplets from a variety of technology, including silicon, indium phosphide, gallium nitride, possibly organic substrates. The number of possibilities is tremendous, and these systems can offer big advantages in terms of size, weight, power, and performance. Now, there's a lot to be done to allow designers to optimize these systems, but today I'm going to talk about how we represent these designs in OpenAccess. I'll start by talking about our past research in this area so that you can get an idea of our perspective and how OpenAccess helped us in the past with those efforts. Then I will talk about a new and much better approach that has been made possible in the last couple of years, along with an example that Ziyu has created. Our work in this area began 20 years ago as part of the DARPA 3D-IC program. There we worked with stacks of 3 silicon on insulator wafers using silicon dioxide bonding from Lincoln Labs. This process included 1 handle wafer that was face up and 2 additional face down tiers that were interconnected using through silicon vias, as illustrated here and on this figure on the right, which is a model that we used to extract interconnect parasitics. Most notably, we created OpenAccess PDKs that were used at our institution and 20 others to create working designs for this process, such as this 3D network on chip example design shown here, which we published at the Custom Integrated Circuits Conference. Another way that we used OpenAccess on this project was to extract high-fidelity thermal models, which we used to understand how heat flowed in the stack. This work was performed by Samson Melamed, who used the earlier version of the Python OpenAccess interface, which was the precursor to the OA script that we all know and love today. Using these results, he developed a new fast thermal analysis technique, which he called high-definition power blurring. Now, what I liked most about this work was that he worked with Rajit Manohar, who was then at Cornell, and his group to do thermal infrared measurements of one of their test chips and compared it to his technique, showing pretty good agreement. None of this would have been possible, we wouldn't have had the time, if all of the design data had not already existed in OpenAccess. A few years later, we had the opportunity to participate on the DARPA DAHI program, which was our first heterogeneous 3D effort. There we designed stacked systems that were assembled by Northrop Grumman Aerospace using their process where they took their own gallium nitride and indium phosphide chiplets and stacked them on top of an active 45 nanometer CMOS chip fabricated by Global Foundries. Again, our goal in this project was to correlate thermal simulations with thermal measurements using a variety of techniques to understand how heat was flowing in the stack. Now, we didn't use OpenAccess at all on this project for a variety of reasons. One was that the thermal simulator was from Siemens using their Calibre 3D thermal simulator. Another was that we weren't involved at all in the PDK development. But the PDK did use a very similar approach to the one that we used on the DARPA 3D-IC project, as I will talk about here in a couple of minutes. The last project that I will mention is the 3D Heterogeneous Multicore project sponsored by Intel. This project, we used a simple face-to-face stack of 130 nanometer CMOS wafers fabricated by Global Foundries using a bonding process from Enhanced Semiconductor that was hybrid silicon dioxide aluminum bonds. One interesting thing about this project was that we had to modify the I/O pads that we got from ARM to allow wire bonding from using a wet etch from underneath the pad rather than the typical method of bonding from the top. Now, we used OpenAccess extensively on this project. Similarly to the 3DIC project, we created OpenAccess PDKs, and we used OAScript extensively to automate the physical design process. We even had to organize the entire multi-project run ourselves and used OAScript a lot in doing the aggregation. This photo up here shows the top and bottom tiers of our design, along with the two tiers for a test chip from Princeton by Naveen Verma's group as well. The left and right layouts were mirrored, flipped along the y-axis, and this allowed us to fabricate both the top and bottom tiers on the same wafer and use them for stacking. Now, because both tiers were fabricated on the same wafer, this stack is not heterogeneous in that sense. Rather, the heterogeneity came from the design. So we designed mechanisms to swap the register file and cache between stacked larger and smaller cores in an effort to show a power performance benefit as we migrated a thread from one core to another, depending on which one was going to execute it most efficiently. We also used OpenAccess to do extensive physical design studies of various traditional 2D planar floor plans to try to get an idea of exactly how much the 3D stacking was benefiting us. We found that there was between 20 and 30% reduction in dynamic power, depending on which way you were optimizing the 2D floor plan. We also did studies showing how this benefit diminished as you increased the pitch above 5 microns for the face-to-face bonds. Now, one of the things I liked most about this work is that it was some of the first to actually show a quantifiable benefit from doing 3D stacking. And again, it was all enabled by OpenAccess. So now let me shift gears and talk about how to create a Techfile to enable these kinds of designs. All of the approaches that I have talked about up until now use what I would call a combined Techfile approach, as illustrated here on the right. That is, you concatenate all of the layers into one Techfile, in which the layer denotes also the tier or chiplet in which that layer is found. In the examples that Ziyu has provided, he shows how to create one of these Techfiles combining 45, 15, and 3 nanometer technologies as shown here. Now, what's new is the possibility of leaving each design in a library attached to the Techfile provided by the foundry. And that's what I'm calling this hybrid Techfile approach as shown here. So let's talk about the pros and cons of each one of these approaches. So let's begin with the combined Techfile approach, which is used most often. Now, on the plus sides, it's very straightforward to implement, and it's also very fast to display or edit each tier or chiplet using a combined view of the stack. And this works in pretty much any open access enabled editor that's out there. So that's pretty good. But it comes with a number of drawbacks. First of all, when you create this combined Techfile, you're essentially forced to duplicate the Foundry PDK, which gives you much more effort and risk that things might go wrong in the process. And if any changes come to the Foundry PDK, or if you change your stacking technology at all, then you're going to be forced to repeat this process, which can be very time consuming and costly. Also, you find with this approach that you're essentially forced to do frequent translations back and forth between libraries that are attached to the Foundry PDKs and libraries that are attached to the combined Techfile, which can be pretty time consuming. And worst of all, if there are any differences in the database units per user unit settings of any of the Foundry PDKs, then The combined text file has to have this setting as the least common multiple of all of the technologies, which means that anytime you move data between, you are forced to scale every single coordinate, which can be very time consuming and error prone. And finally, because the layer name has to indicate the tier or chiplet that it's on, these names can get to be very long and difficult to distinguish, since most of the editors out there don't intend to be used with layer names that are quite so long. So that's a lot of downsides. But like I said, it's this approach which has allowed us to come as far as we have with 3D designs. If you want to play around with this approach, I can recommend two demonstrations. First, being this FreePDK 3D 45, which you can download from our website. It's basically a stack of 5 tiers of our 45 nanometer PDK using a stacking approach that's similar to the one used by Lincoln Labs. And that's illustrated over here, this image on the right. The second is actually a demo script developed by ZU that combines the 45 nanometer, 15 nanometer, and 3 nanometer versions of the FreePDK into a combined text file. And you can ask Marshall Tyner how to download that one from SI2. So now let's talk about the hybrid text file approach. This approach requires no duplication of the Foundry PDK, and so it's much less effort and risk. There's also no constraints on the dBu per UU settings of each technology, so there's no scaling of layout. There's no translation of layout at all with this approach, and the layer names are short and easy to distinguish. What enables this approach are these so-called adopt and release methods to switch the text files on the fly. That means that you create cells that contain instances from multiple text files, and then reattach the technology library for the library that contains those instances on the fly before you add each instance. You also need to do this reattaching each time you do any transformation on any of the coordinates in any of those of any of the shapes in those instances. So this process of reattaching does add some complication, and because of that, it's likely to be slower to display and process. We don't know how much slower yet because we haven't investigated it, but we know it's not going to be zero. Also, there's enough complication with this approach that you have a significant amount of effort required to build it in to every single tool that's going to touch this layout in your whole design process. And that is complicated enough that I don't know anyone that has done it. I don't know of any layout editors existing that use this approach currently. What we do have is some very nice example code from ZU that demonstrates this process. What he's given us is some Python OA script to create a cell that contains instances from libraries in 45 nanometer, 15 nanometer, and 3 nanometer technologies. Then he has some code to traverse the hierarchy of each instance, plotting every shape contained within that instance in Matplotlib. So this is nice because it demonstrates how and when you need to reattach the text file to add instances and transform the shapes. Now, a couple of caveats here. First of all, the nesting is only one deep. So for example, we haven't tested it yet on an example where you've got, say, a 3 nanometer instance within a 15 nanometer instance, which is itself contained within a 45 nanometer instance. The code's there to do it, but it just hasn't been tested yet. And secondly, it currently assumes that all the tiers are face up. ZU got started with the code to handle face down tiers, but he simply didn't have time to finish it. I think it should be straightforward to do, however. So here's some example code to illustrate ZU's recursive routine for plotting an instance. He passes the current instance along with the current technology and the combined transform for all higher levels of hierarchy. And then he opens the block for the current layout. Then he checks the technology of the current instance to see if it's different from the technology that's currently being processed, and if so, then it attaches the top level library to the instance's technology. And then it goes through every shape and calls a transform on the coordinates in that shape. From here, it goes on to add patches in the plot for every single shape type and traverse all of the other instances by calling this function again. My hope is that this example will encourage people to start applying this hybrid Techfile approach. Now, to complete the process, we also need something that specifies a chiplet's facing and technology. And from what I know of TSMC's 3D blocks format, it would be a great way to do that. If we could get more tools that use this combined open access 3D blocks Techfile approach, then I think it would go a long way towards streamlining and simplifying the stacking process. And I'm just going to throw this out there. Why not create a viewer or editor for such a database? There's probably complications we don't know about, but from what I know, the technology seems to be there, and it would be a great benefit. So in conclusion, OpenAccess has been a big part of getting us to where we are today with 3D design, but it has some significant drawbacks. OpenAccess is ready today for us to start building a more convenient hybrid Techfile approach into our tools, as shown by Zhu's demonstration. But we do need more vendors to take a leap and to start implementing it into their tools. So this concludes my talk, and thank you very much for your attention.